All right, today we are diving into a really fascinating puzzle that's right at the heart of computational science. It's this one single mysterious piece that scientists have been trying to figure out for decades. So, yeah, let's get right into it. So, let's just start with a big question. When you're trying to calculate the total energy of a material, down to the electron level, what's the one piece of that puzzle that you just can't know for sure? It sounds kind of weird, right? How can you do science with a big unknown staring you in the face? Well, that's exactly what we're going to unpack. The main goal here, using this incredibly powerful method called density functional theory, or DFT, is to calculate the total energy of all the electrons in a system. I mean, think about it. If you can do that with real accuracy, you can predict how materials will behave, you can design new drugs, create better batteries, pretty much anything. It's that fundamental. To get that total energy, we use what's called the Kohn-Sham energy equation. And the easiest way to think about this equation is like it's a recipe. It's got three main ingredients you need to add together to get your final result, that total electronic energy. Two of them are pretty straightforward, but the third one, well, that's where all the messy reality of quantum mechanics is hiding. And here is the twist. It's a recipe where we know the exact measurements for two of the ingredients, but that third one is a total mystery. We know it has to be there, we know it's absolutely crucial, but we just don't know its exact form. So, what are the parts we do know? Well, first, you've got the kinetic energy of the electrons, but it's calculated as if they weren't interacting with each other at all. The second part is the electrostatic energy, the classic push and pull between the negative electrons and the positive nucleus and between the electrons themselves. These parts, we can calculate them precisely. They're well defined. And that brings us to the mystery ingredient, the exchange correlation energy, or EXC. This is basically the everything else bucket. It bundles together two really complex quantum effects. You've got exchange energy, which is this strange quantum rule that says two electrons can't be in the same state, so they act like they're avoiding each other. Then you have correlation energy, which is more intuitive. It's how electrons actually dodge each other because, their negative charges repel. And this is the absolute key, because X is trying to capture this impossibly complex dance of every single electron interacting with every other electron all at the same time. Its exact mathematical form is just not known. It is the fundamental challenge in all of density functional theory. Which leads to the obvious question, right? If a huge part of your master equation is a total unknown, how on earth do you get a useful answer? How can this possibly be one of the most widely used tools in all of science? Well, the answer is both super simple and kind of profound. You don't find the exact answer because you can't. Instead, you approximate it. Scientists have spent decades developing these brilliant, incredibly sophisticated ways to make an educated guess for that missing piece of energy. And that is where we get the term functional. An exchange correlation functional is the specific mathematical tool, the specific approximation that you choose to calculate that unknown XC energy. The whole game, really, becomes about finding the functional that gives you the best possible, good enough guess for whatever you're studying. Okay, so how do you even start making these approximations? I mean, they're not just random shots in the dark. They're built up in layers, starting with the most foundational category out there, which are called semi-local functionals. The two big ideas in this family are the local density approximation, LDA, and the generalized gradient approximation, GGA. Think of it like describing the weather. The simple LDA approach is like standing in one spot and only reporting the temperature right where you are. But the GGA approach is smarter. It reports the temperature where you are, but it also tells you if it's getting hotter or colder as you move around. That's the gradient. And that extra little bit of information about how the electron density is changing, it gives you a much more complete picture. So let's zoom in on the original, the one that really started this whole thing, the local density approximation, or LDA. It's the simplest way to tackle the XC problem, but the idea behind it is actually pretty brilliant. So how does it work? Well, LDA looks at the electron density at one tiny point in a molecule, and then it makes this massive assumption. It basically pretends that that point is floating in a huge, perfectly uniform sea of electrons, a homogeneous electron gas that has the exact same density. Now, that's an idealized world for sure, but it's a world that scientists can solve perfectly, so they just borrow that perfect answer and apply it back to that one single point in the real molecule. And here's the thing, even with this one LDA approach, there are different flavors. Scientists can tweak the math for the exchange part and the correlation part separately. And what you get is a whole family of LDA functionals, each one with a slightly different recipe. But the key thing to remember is they all share that same core idea. You approximate the real world by using this idealized, uniform sea of electrons. So, if you take one thing away from all of this, let it be this. The exchange correlation energy, XC, is the central unknown puzzle at the heart of density functional theory. And the functionals, these clever, constantly improving approximations, are the keys that scientists are building to try and solve it. Which leaves us with a final, really fascinating thought. The hunt for better functional is one of the biggest quests in all of computational science. So if every new approximation gets us just a little bit closer to the true energy of a system, what incredible discoveries are just waiting to be unlocked by the next great functional? What new materials or medicines or technologies are just hiding beyond our current ability to calculate? The puzzle isn't solved yet, and believe me, the search continues.